Go over some inequalities and then talk about the law of large numbers. Let's take a look at the following proposition. This is what we proved before, basically just going over the review. This is called Markov's inequality. If x is a random variable, then for any positive number like a, the probability that x is more than or equal to a is going to be less than or equals to the expected value of x divided by a. The proof is very easy. Let's take a look at the short proof, sketch of the proof. Let x be a continuous random variable with density function f of x. Then, as you remember, the expected value for x can be written as the improper integral 0 to infinity of x divided by f of x dx. This can be written as 0 to a x times f of x dx plus the integral a to infinity of x f of x dx. So obviously, this integral, when you add these two together, is more than or equals to the integral a to infinity of x f of x dx. So basically, since x ranges between a to infinity, it is more than or equals to the integral a to infinity. Now I'm going to just use a. So you see, I did the substitution here. F of x dx. And this guy can be written as a times the integral a to infinity of f of x dx. But this is nothing but a times the probability that x is more than equals to a. So we just showed that a times the probability that x is more than equals to a is less than equals to e of x. If you do the division, the probability that x is more than equals to a is less than equals to the expected value of variable x divided by a. And this is the proof that we were looking for. Now let us talk about Chebyshev's inequality. We talked about this before, but just a review for you. Another proposition for you. Chebyshev's inequality. Basically, if x is a random variable with mean to be mu and the standard deviation to be sigma, then, as we saw before, for any value of k to be positive, the probability of the distance between the x and mu is more than equals to k, so less than equals to sigma squared divided by k squared. Let's go over a sketch of the proof. Obviously, x minus mu to power 2 is non-negative variable. So if we apply the Markov's inequality, now basically set a to be k squared. Take a look at the inequality that we discussed up here. Just take this one. So we have the probability that x minus mu to power 2 is more than equals to k squared. It's going to be less than or equals to expected value of x minus mu to power 2 divided by k squared. Also from algebra, remember that when we are saying that x minus mu to power 2 is more than equals to k squared, it means that absolute value of x minus mu must be more than equals to k. So equivalently, we can write it this way. The probability that the absolute value of x minus mu is more than or equals to k. This is less than or equals to the expected value of x minus mu to power 2 divided by k squared. But as you remember before, the expected value of x minus mu to power 2 is nothing but the variance, and you divide it by k squared. This is already here. So we just prove the Chebyshev's inequality using algebra and the Markov inequality. Now let us talk about the weak law of large numbers. Our theorem, the weak version of law of large numbers. So in this theorem, we're going to introduce a sequence of independent random variables. Let x1, x2, xn be a sequence of independent variables with the same distribution. The expected value for each random variable is mu. Then for any positive epsilon, the probability that the difference between x bar and the mu is more than epsilon as n goes to infinity approaches 0. So basically, what does it tell us? It tells us as the sample size, which is n, increase the probability that the sample mean differs from the population mean, which is our mu, by more than epsilon approaches 0. Let's take a look at the sketch of the proof, everybody. For the sketch of the proof, we have the following case. The expected value of the sum, which is basically the expected value of adding all of these variables together and divide them by n, is nothing but mu. And remember that when we talked about the variance, this is the variance of the summation of these values divided by n. And this is sigma squared over n. Now take a look at the Chebyshev's inequality. If we replace x by x bar, see what happens. And your k is nothing but your epsilon. So let me just take this one and copy and paste it down here by Chebyshev's inequality. We just do the simple substitution, the probability of the absolute value of x bar minus mu, the difference between the sample average and the population mean, is more than or equals to k, which in this case you can replace it by epsilon, is going to be less than or equals to sigma squared over n. So in this case, we're going to have n times the epsilon squared. Again, remember from sampling distribution of sample means, here we have to do the replacement instead of having just sigma squared. This sigma squared down here is replaced by sigma squared over n, because we are dealing with the sampling distribution of sample means. So that's how you end up with sigma squared divided by n.